Welcome back to the podcast, where we delve into the captivating realm of distributed systems. Today, we're focusing on a fundamental concept that ensures the reliability and consistency of these systems: consensus. You might wonder how difficult it can be for a few nodes to come to an agreement. But the truth is, it's a lot more complicated than it seems. We'll unpack the nuances of consensus, its significance in distributed transactions, and the various challenges that arise when nodes need to agree on a single outcome. So grab your headphones and let's dive in. To start, let's establish what we mean by consensus in distributed computing. At its essence, it's about getting multiple nodes to agree on a specific value or state. It sounds straightforward, but the complexities quickly become apparent. When network connections are disrupted or nodes fail, reaching consensus can turn into a significant challenge. Picture a scenario where two nodes both think they're the leader of the system. This is what we call a split brain situation. When both nodes accept rights, their data can diverge, leading to inconsistencies and potential data loss. This brings us to the concept of atomic commit, which ties closely to consensus. In an atomic transaction, all participants must agree to either commit or abort the transaction. If just one participant needs to abort, the entire transaction has to roll back. This is where consensus becomes critical. We need a reliable way to ensure that all nodes are aligned. Either they all succeed or they all fail. You might have heard of the flip result, named after Fisher, Lynch, and Patterson. This theorem demonstrates that in an asynchronous system, where nodes can crash and messages may be delayed, there's no algorithm that can guarantee consensus. But don't let that discourage you. In practice, distributed systems frequently manage to achieve consensus, especially when we incorporate timeouts or other mechanisms to identify suspected failures. Now, let's take a closer look at the atomic commit problem and one of the most common solutions, the two-phase commit or 2PC protocol. This algorithm is widely utilized in databases and messaging systems to handle distributed transactions. Here's how it works. When a transaction is ready to commit, a coordinator sends a prepare request to all participating nodes. Each node then responds with either a yes or a no. If all nodes respond with yes, the coordinator proceeds to send a commit request in the second phase. If any node says no, the coordinator tells all nodes to abort. You can think of it like a wedding ceremony. The officiant asks both partners if they want to marry each other. If both say "I do," the ceremony continues. But if either partner hesitates, the ceremony is called off. This ensures that the commitment is atomic. Everyone is either on board or no one is. However, it's essential to recognize that 2PC has its drawbacks. While it provides a mechanism for achieving consensus, it can be inefficient and susceptible to certain failure scenarios. For example, if the coordinator crashes after receiving all the yes votes but before sending the commit request, the system could end up in an uncertain state. This uncertainty is one reason why some distributed systems have turned to alternative consensus algorithms like Raft and Paxos, which aim to address these limitations. It's also worth noting that while 2PC is a consensus algorithm, it's not the only option available. There are various approaches to achieving consensus, each with its own trade-offs. For instance, non-blocking atomic commit presents a more complex challenge than consensus itself, but it's crucial for specific applications where availability and performance are paramount. As we draw our discussion to a close, it's important to emphasize that consensus isn't just a theoretical concept. It has tangible implications for the reliability and consistency of distributed systems. Whether you're developing a database, a messaging system, or any application that relies on multiple nodes, grasping how to achieve consensus is essential. In summary, reaching consensus in distributed systems is a complex yet vital challenge. From navigating the split brain problem to understanding atomic commit and the intricacies of the two-phase commit protocol, the path to ensuring all nodes agree is filled with obstacles. Yet, with the right algorithms and strategies, we can effectively tackle these challenges. Thank you for tuning in today. We hope you found valuable insights into the world of consensus. Don't forget to subscribe for more discussions on distributed systems and their fascinating intricacies. Until next time, keep exploring and questioning the technology that surrounds you.